Thank you again. So our second paper, again, my pleasure to present towards the Unified Cybersecurity Testing Lab for satellite, aerospace, avionics, maritime drone, or shortly SAAMD technologies and communications. Again, work at JYU in collaboration with Turtiainen, Kanter, and Hämäläinen. So similar style agenda, background problem statement, related work, methodology results, future work, and our summary contributions. So the main background of this work is, well, we've been doing this research for a couple of years, and of course we accumulated a lot of research on different protocols that were not necessarily initiated by space security or space research, but somehow they all unite together into space, so I would say. Because satellites process or pass through or collect or aggregate and then relay a multitude of critical protocols, all critical for their own verticals. For example, in aviation, there's ADS-B with their 1090 extended splitter and UAP 978 in US and ACARS, at least. Then there's the maritime protocols such as AIS. The previous paper I have shown that search and rescue systems such as COSPAS, SARSAT with their EPRB, ELP, and PLBs. And there are many others, of course, critical protocols such as GPS and CCS, DS, and so on. And the idea is that, of course, for GPS, it is clear that there are space satellite systems and CCS, DS. Similarly, for ADS-B, ACARS, and AIS, it might not be immediately relevant that there are space and satellite systems, because you might think, or somebody not aware might think they're just aviation or maritime, but of course, in places where there are no ground stations or no other stations to get the data, it goes through the satellite. So there's always some kind of receiver on ADS-B and ACARS and AIS. So they still process both. And we have seen in the past, time and time again, for example, that aviation, including ADS-B and ACARS, have been shown vulnerable to different types of attack. This is just a very short list and, in a way, a little bit shameful self-citation here. But our Ghost in the Air started 2012, and then the ACARS by Tesla in 2013, and I know Martin and his group were doing crypto attacks on ACARS as well. Then we also performed the more software level attacks on over ADS-B communication channels and fuzzing in 2022. And we have shown that the aviation is vulnerable. Similarly, the maritime AIS protocols have been shown vulnerable over the past decade, started by Balbuzzi mainly with their first evaluation of AIS. And then we've continued this work recently with similar software logic fuzzing and attacks and crashes on AIS devices and software. And then, as hopefully I convinced you that the search and rescue and COSPAS SARSAT is not very far away from ADS-B, ACARS, and AIS in terms of being quite vulnerable and quite insecure. In many similar ways, and but it suffers from the same basic flaws of being designed in the 70s, 80s, 90s, and lack of security. So besides that, we have just accumulated a lot of gear over the years and a lot of insights that how these methodology works, as Martin asked in the first paper, but well, the methodologies are essentially the same, and usually when the methodologies are the same, like makes sense to unify them. So the first research question we try to answer in this paper is what is the state of the art in cybersecurity labs and testbeds that relates to space or are centered one way or another around space systems, and ideally unifying all intertwined fields such as space, satellites, aviation, maritime drones, etc. The second research question we try to answer, or at least provide evidence of, is the feasibility of and the budget of building and expanding all cybersecurity lab and testbed, focusing on space or serving space security needs. And then the final research question, what are the attacks can be implemented and what are the results of demonstrating such attacks in the lab? So this is a summary of the closest related work that are relevant to this paper. And in many ways, they're our current paper, but I'm presenting, and there are 3 other works. And I say, but I'm happy that somehow our paper at the same time competes friendly with Martin's and his group's test lab, but they presented at CSET, Computer Security Experimentation Testing Workshop recently. And at the same time, it complements each other and extends, as I will explain later. There's also the recent work by Predescu, also late 2022. They focused on R-Ring 429 and R-Ring 664, communication and buses. There's also the work of Dave that focuses mainly on drones and some drones/GPS communication. Now, I think I would like to say that Martin's and his work and his group's work in many ways are similar, but they do a lot of aviation, and they expand also a little bit to from the analysis of the paper we did. They expand into satellite and SATCOM. They have very strong GPS compared to our lab, for example, very strong GPS setup and higher RF shielding type of setup. In our case, we focus a lot on covering ADS-B, electronic flight bags, ACARs, basically the whole area, while in Strockmeyer's case, they focus on complementary systems such as collision avoidance system, TCAS, and CPDLC, data links. On the satellite systems, we are not necessarily looking at SATCOM, but we are interested in the, as I mentioned, EPRB, COSPAS, SARSAT, CCS extending to CCLDS, and especially on all these layers, we focus on the software, firmware, fuzzing those devices and fuzzing those firmware softwares and detecting the crashes or remote code execution, not just protocol attacks as spoofing and replay, for example. So the methodology is quite, again, pretty much similar. We don't reinvent the wheel. The lab that we set up follows the basic rules that there's a Faraday RF isolation box, and we also have RF leakage metering. And then inside that, we have the, let's say, experimentation platform and devices, that is the laptop presented here. It can be any arbitrary general computing device, laptop or server. We have the SDRs depicted here. We've put just each one of them, but we have several, about 4 Blade RF, different hardware versions, and we have about 4 Hack RFs, again, different hardware modifications as well. We also have different Android and iOS phones for the purpose of running different client-side software, such as the applications that pilots will put on their iPads or Android tablets and so on. And also, besides that, the platform runs on the laptop. The laptop can also be used for running the client-side software, such as the EPRB or PASS SARSAT rescue software on the simulating MCC or RCC. Then we have, again, a growing list of devices that we've collected over the years. Again, we showcase them and enumerate all their names and capabilities in the paper. There are big, long tables for interested readers. But our biggest direction is on the Avionics and ADS-B, meaning 1090 extended tweeter and UAT 978, both ADS-B in and ADS-B out. Some of them are just ADS-B in, some of them are both ADS-B in and ADS-B out. Or so we have a lot of different types of scenarios that we can test. Then we have the Maritime part, where we have the commercial transponders. We have commercial receivers that are connected to various data buses on ships or yachts, such as QK A027. Still some more work could be done there. We haven't did too much there. And then we have the DJI and Enterprise 300 RPK as an example of drone to which we can connect ADS-B sensors and devices, and then do more complex attacks on drones via ADS-B and similar. We have also the satellite system that runs CCSDS, and we can also implement, for example, COSPAS, SARSAT, EPRP on some of that board as an extension for our work. And we have some example of this COSPAS McMurdo device. So again, this is just supposed to be a list to show the capabilities of our current lab. And again, as I mentioned, we built it across a couple of years, under 100K of total budget. And we keep expanding it towards space and avionics and maritime additional systems. Main results that we've achieved with this lab is, for example, I'll try to enumerate. First of all, we've been able to move very fast in terms of about 7 papers that are related to space, or protocols that are related to avionics, maritime, and space, one way or another. So for the ADS-B, we've tested fuzzing, the denial of service attack, crashing, potential remote code execution, and arbitrary code execution. So in some cases, we tested 36 configuration, 12 attacks, and caused denial of service by remotely crashing or impacting more than 50% of the test set. In another case, we've tested the mobile cockpit information systems, or slash electronic flight bag applications on Android and iOS. So we've tested in total more than 68 configurations for 1090 and 978 in total. And we see that for 1090, we have impact on 63%, and UAT 978, we have impact on more than 37%. Again, impact means a denial of service, like the software or device crashes, or just hangs, or there's completely abnormal behavior. So it means some memory problems or some other types of issues. Oh, sorry. Then we have similar results with AIS, where we tested 19 configuration, more than 89% are impacted. So we can see that in AIS, the quality, well, the test set is smaller, but the quality lags behind compared to ADS-B, maybe because of lack of awareness compared to ADS-B. More importantly, we have been able to demonstrate the infamous Log4j vulnerability, CV 2021-44228, and related CVs. But we are able, with the lab, basically the software and the devices we have, we've demonstrated that we can achieve a Log4j exploitation over ADS-B, ACARS, AIS systems, and we are looking forward to experiment with it on COSPAS, SARSAT, and CCSDS. And then the first paper that I presented today, the COSPAS, SARSAT, is also implemented using this lab, and dump 1030, which is equivalent of dump 1090, but for the uplink capabilities of ADS-B. So I've already mentioned some future work. We want to develop and support for additional technologies, CCSDS, FLART for drones, and remote ID for drone UAV, study more protocols and more complex scenarios, how these protocols circulate between these devices and reach the ground station or different control centers. So we introduce and detail our unified lab. We demonstrated its effectiveness with a handful of peer-reviewed papers with quite good results in terms of security detection of vulnerabilities. And we invite international collaboration for lab usage, for lab experimentation, expansion for different additional protocols or devices. And yeah, thanks. I'm open to questions.
It's a testbed, right? So how can other people use it, basically? It's a really nice collection of different, well, hardware and software setups.
Yes. I think it's definitely not some of those test beds that can be completely used remotely autonomously because of the types of protocols and the data they could potentially send. But please do reach out to us, and then we can explain step by step. It's essentially if you want to visit the lab, or you want to send the device, or you explain what protocol do you want to test, and then we can take it from there. But I mean, we have a very simple way to bootstrap collaboration. If there's an additional device being involved and needs to be shipped, I mean, that's more like a logistic question, but is easily solved. If you need some data, then of course we can also generate that or things like that. So I'm not sure if that answers your question, but I think understanding the exact needs, or whether it's a research need or industrial need, then it's good to contact directly, and then we take it from there.
Is it possible to extend the testbed to include functionalities that only a subset of the environments operate in? I would imagine, for instance, avionics and space applications have a lot of overlap in terms of, atmospheric scattering or something like that aren't necessarily valid for maritime applications. And so maybe maybe not having a full encapsulation of every or a common set of tools that are common to all environments, but maybe a subset of multiple environments.
Well, I try to understand if I got your question right. First, the test bed and the lab, we don't offer, for example, environment configurations such as maybe ray influence on avionics and hardware, things like that. So we operate the lab and the test bed, let's say, from protocol communication, software, and RF point of view. So we cannot, at this point, we don't have the lab or the capacity to influence, let's say, the environmental things, and we also don't do GPS. I mean, we could add also GPS influencing through the use of additional SDRs, but that's wasn't the core point of our lab. But in terms of understanding your original question, we can definitely set up the lab and the test bed in such a way, for example, for the transmitter to transmit the particular data that is needed for the test, whether it's a functional test or cybersecurity test. So for functional test, maybe it needs to test minimal operational specification, what's called MOPS in ADSB or in many of these RTCA standards. And of course, if there's a need to test a particular avionics receiver, but definitely we've been doing this with almost a dozen of those receivers, and excludes the AIS. So they are not all monolithically put together, but of course we can put them in a more complex environment if that is needed. For example, put ADSB relay or aggregation on the satellite, but I've demonstrated, and then use that to transmit the data further to a ground control station, which runs a particular software on the laptop or on some server, and see the whole chain of potential exploitation, so to speak. It's a long answer, but I hope it answers your question.
You mentioned the CCSDS protocol stack. how far are you? Do you already have partial implementation on GitHub or so? We are interested to collaborate with people that would contribute to an open source implementation of the protocol stack.
That's a good question. So we take our foremost priorities is to try to implement minimal codecs, coder and decoders, so that it enables us to do effective and efficient fuzzing of the protocols to find the vulnerabilities or implementation flaws in existing binaries or source code. We don't have like a very strong CCS, DS, let's say software engineering expertise at the moment, or any particular extension to CCS, DS to contribute. But definitely we are interested also in the space, but if there is a particular extension or a particular stack of CCS, DS out there and somebody owns, but we take a look, of course, we are happy to hear and work together on that.